Okay, so this evening we are going to be looking at motion of a box on an inclined plane, which is a flat surface that is tilted at an angle. Usually, inclined planes are tilted at an angle which is less than 90 degrees. So in this case, you have something like this. So this is what we are looking at. So our interest is to study how an object of mass m would move along this inclined plane. So that's what we are interested in. Recently, we have been studying the motion of an object. We have studied the motion of an object on a flat surface. We have looked at that. So we're going to apply the same logic to the case where an object is on an inclined plane like this. Inclined at an angle theta in this case. So what we are going to do is, of course, we are going to put our box of mass m on this inclined plane, and this inclined plane makes an angle theta. Now, this box, as you are all aware, the box has got mass m, and because of this mass, this box has got weight. Because of the mass which the box has, this box has a value of weight. The weight of the box is given by the mass of the box multiplied by the acceleration due to gravity, and the weight is pointing downwards along this line. Always the weight of anything with mass m points downwards. The next thing, if we are to make progress, we know that it's a couple of things are possible. Okay, it is possible that this box can just stay where it is here without moving, but the other case which can happen is that the box can actually move, and in a case like this, the box will tend to move downwards with increasing velocity. So there's going to be acceleration in this case. The box can move downwards very fast with increasing speed, or it can stay where it is. So if we are going to study the motion of this box by trying to use Newton's second law of motion, we need directions. Which direction is going to be our x-axis? Which direction is going to be our y-axis? Since the box tends to move down, in this case, so the box is going to move down parallel to the incline, we choose this direction which is parallel to the incline to be our horizontal direction, or to be our x-axis. So the direction which is parallel to the incline, we choose this to be our x-axis. That's the first thing we do. We have to make a choice about directions. Since we are dealing with forces, which direction is the x-axis, which direction is the y-axis? So we are choosing the direction parallel to the incline to be our x-axis, and we are choosing the direction which is perpendicular to the incline. Yes? What is the problem?
Sir, the audio is cutting. The audio is cutting. It's just bumping. I don't know, maybe it's me here or maybe it's same for everybody.
I don't know. I'm just in my office. Okay. So, like I've said, we choose the direction which is parallel to the incline to be our horizontal direction, or our x-axis. Since this is going to be our x-axis, we know that an x-axis has got a positive x-axis and a negative x-axis. So after choosing this direction parallel to the incline to be our x-axis, the next choice we make is which one is going to be our y direction, or our vertical direction. So we choose the direction which is perpendicular, a direction which is 90 degrees to the incline. So our incline is this one. So 90 degrees to the incline, which is in this direction, that is what we choose to be our y direction, or vertical direction. So we have our x direction parallel to the incline, then we have our y direction perpendicular to the incline. The next choice you have to make about the x axis is which part of the x axis is going to be positive and which one is going to be negative. That is very simple. Always choose the direction in which the box is likely to move to be your x direction. So in this case, in this situation where you have a mass on an incline, the most likely thing which is likely to happen is that this box will move downwards. So we choose the downward direction to be our positive x-axis, meaning that the opposite of that is going to be our negative x-axis. So any vector which will point in this direction, that will be our positive x-axis. Any vector which will point in that direction, that will be our negative x-axis. So vectors pointing along the positive x-axis, will treat those to be positive. Any force pointing along the negative x direction will be treated to be negative. The other choice we make is which direction is going to be our positive y and positive x. So any force pointing, we choose above the incline to be the positive y and below the incline to be the negative y. So any force which will point above the incline, that is what you're going to choose as our positive y, and any force which will point below the incline, that is what we're going to choose as our negative y. Now, this choice of x-axis and y-axis presents an interesting situation, in that if we stick to this choice, parallel to the incline, x-axis, perpendicular to the incline, y-axis, you notice that the weight of the box, this weight, will not point along the x-axis. It will also not point along the y-axis. So the weight of the box, which is pointing down as the weight of any object is supposed to do, will point neither along the x-axis nor along the y-axis. So the weight is not pointing along the x-axis, and the weight of the box, which is Fw, is not pointing along the y-axis. However, there is a part of the weight pointing along the x-axis, and there is also a part of the weight pointing along the y-axis. How do we know that? We simply have to ask the question, how much of this weight, mg, is pointing along the x-axis, which is this direction, parallel to the incline? Then how much of this weight is pointing along the y-axis, which is perpendicular to the incline? The how much of the weight is pointing along the x-axis is the x component of the weight. The how much of the weight will point along the y-axis is the y component of the weight. So with that in mind, you will quickly notice that along the y-axis, this y-axis, so the y-axis is perpendicular to the incline, you can break this weight mg into a component which is equal to mg cos theta, which is along the y-axis, and mg sin theta, which is pointing along the x-axis. So this weight can be split into components mg sin theta and mg cos theta. So in this case, if you have an incline like this, the angle of the incline is also equal to this angle here. So using the same angle theta, which is going to be this angle here, you have the resultant force, which is the weight, or you have got the vector, which is the weight here. No, you have got the weight of the box, which is mg. Then this weight of the box, you can find out how much of the weight is along this line. And as you can see, it is pointing down. So this is the y component of the weight, mg cos theta. And along this line, which is the x component of the weight. These components, as you can see, they have dashed lines. That's how you denote a component. A component is dashed, okay? The actual vector itself is a solid line, okay? Then at the end, you see an arrow there. There's an arrow at the end of the components. This is telling you that components are also actually vectors, with the exception that we know precisely in which direction these components are pointing. So in our case here, the x component of the weight mg becomes the opposite of this triangle. Since our x component is parallel to the incline, so the component which is parallel to the incline becomes mg sin theta. So this becomes our x component, and the component which is perpendicular to the incline becomes mg cos theta, which becomes the y component. So this component, mg sin theta, is what causes the box to move down. The box shows a tendency of moving down. It's because of this mg sin theta. So this is the portion of the weight which pulls the box downwards. Apart from pulling the box downwards, the weight through its y component, which is mg cos theta, tends to exert a force on the incline. Now, when the box exerts a force on the incline through mg cos theta, the incline is not going to be happy. Since the incline is not going to, it's not going to, as much as it's going to be happy, but will not overly react, the incline is going to push back the box with a normal force which is equal but opposite to the y component of the weight, which is equal to mg cos theta. So basically that's what happens. Now the other thing you have to notice also is that you have got this mg sin theta, which tends to pull the box down. Since the box will tend to be pulled down, there has to be another force which is going to oppose the motion of this box, which is the friction force. So the weight of the box gives us two forces. It gives us the force which is pulling the box downwards along the incline, which is mg sin theta. It also gives us part of the weight of the box exerted on the incline, which is mg cos theta. And because of this mg cos theta, the incline won't be happy, so the incline will push back against the box, resulting in a normal force. This mg sin theta will try to pull the box downwards. As the box is being pulled downwards, there's going to be friction which is going to oppose the movement of the box. So with that in mind, what you actually end up with is a situation like this. This is what you end up with. You have the weight, which is mg. Then the weight of this box is split into components. There is the y component of the force, which is mg cos theta, which is this one, pointing down, exerting a force downwards on the incline. Then the incline is not happy. The incline is pushing back with the normal force, which is denoted as Fn here. Then the x component of the weight, which is your mg sin theta, is pulling the box downwards like this. Then there is a force of friction, which is this one, which is going to oppose the movement of a box going downwards. So in this case, we have two forces, mg sin theta pulling the box down along the incline. Then there is a friction force which is pointing up, which tends to oppose the movement of the box. There is the weight of the box, mg cos theta, exerting a force at 90 degrees to the incline, and the incline is not happy, so the incline is pushing back with an equal and opposite force. Is this clear? Is it clear what has happened to the force? The weight of the box? How we have split the weight of the box along the directions I've chosen, along the x-axis and along the y-axis? Sorry? Where what?
So the friction is opposing the box when it's spinning, when it's the force that's pulling it down. Now the friction part. Can you repeat that part?
This box will move down because of this force, mg sin theta. A box on an incline, if you leave it there, it will never on its own go up. It will tend to come down. Either it will stay there or come down. If you put the box on an incline, you will not find the following day that it has moved further up the incline. No. Most likely to move down. So if the box has a tendency to move down, then friction has to point in the opposite direction, opposing the motion. That's why the friction is pointing this direction. Is that clear?
Yes, sir.
So the friction always opposes. If the box is going to move down, friction is going to move up. If the box moves up, friction is going to point down. Any other questions? With this breakdown of our forces, the weight here, mg, is pointing neither, because we have made a choice to say parallel to the incline, this is going to be our x direction. Perpendicular to the incline, that's going to be our y direction. So you can clearly see that the weight of the box, which points downwards here, neither points along the x direction nor points along the y direction. That's the first thing, because of the choice of direction we have made. Along the incline as our x direction, parallel to the incline as our y direction. That choice of direction leads to us realizing that the weight of the box neither points along the x direction nor along the y direction. However, we ask the question, how much of the weight lies along the x direction? That is your mg sine theta. How much of the weight lies along the y direction? That is your mg cos theta. So the y component of the weight is mg cos theta. The x component of the weight is mg sine theta here. So with this mg sine theta is the one which will put the box down. Since the box will be put down, there has to be friction opposing the movement of the box pointing up. Remember, we have chosen the direction in which the box is going to move, which is downwards, to be our positive x direction. If the direction in which the box is moving downwards is our positive x direction, then the opposite direction, which is upwards, is going to be our negative x direction. We have also chosen the direction above the incline to be our positive y direction, which is the direction in which the normal force is pointing, meaning that in that case our normal force is going to be positive, but the y component of the weight, which is pointing below the incline, this is going to be a negative force as a result of the choices we have made about direction. Which direction is the x direction? Which direction is the y direction? Which one is the positive x direction? Which one is the negative x direction? Which one is the positive y direction? Which one is the negative y direction? Direction is everything. Are we clear? Direction is everything when you are looking at resultant forces. Okay, so let's start with the resultant force along. Let's start with the resultant force along the y direction. So along the y direction, which is this direction, there is this normal force pointing up in the positive y direction. Then there is also the y component of the force, which is mg cos theta, pointing down, which is the negative x direction. So we've got a positive normal force, then we have got a negative y component, which is mg cos theta. So there are only two forces acting along the y direction here. So our resultant force along the y direction, the summation of the forces along the y direction, is going to be equal to the normal force plus the negative x component of the weight, which is minus mg cos theta. So we end up having our resultant force along the y direction being equal to the normal force minus mg cos theta. So this is our resultant force along the y direction. Now, if the only thing this box is going to do is slide on this incline, meaning that the box does not jump up and down, it just slides, it means that there is no acceleration along the y direction. The position of the box along the y direction does not change. Its velocity also does not change. So if the box is only sliding down or just stays wherever it is here, if the box decides to stay there or slide down, along the y direction, the position of the box will not change. Since the position of the box does not change, then the acceleration along the y direction is going to be equal to 0 meters per second squared. That's what the acceleration is going to be. So along the y direction, we know a couple of things. We have found the resultant force to be the normal force minus the y component of the weight, which is mg cos theta. We also know the acceleration, that since the box is only sliding, or staying on the incline without jumping up and down, the acceleration along the y direction should be equal to 0. So this, so ay in this case is going to be equal to 0. So this 0 multiplied by the mass gives you 0. So the mass of the box multiplied by an acceleration of 0 gives you 0 this side. So we replace with the resultant force, which is we have here is Fn minus mg cos theta equals to 0. So if this is 0 this side, then you can take this minus mg cos theta to the other side. So what you end up with is the following. You end up with the normal force being equals to mg cos theta. So the normal force with which the incline is going to push back against the box is going to be equal to the y component of the weight, which is mg cos theta, but negative in direction. And that is what we have seen about normal force, that the normal force is always equal but opposite to the weight, to the force, or the weight of the box if it's flat. But in this case, it is equal but opposite to the y component of the weight, which is mg cos theta. That is our normal force. Are we clear about this? So on an incline, there's a difference. There's an added part. There is a weight. This is a weight. But there is this part which is added, the cos theta. That is because of the incline. So the normal force becomes equal to the weight of the box multiplied by cos theta, which is the y component of the weight. Is it clear? Hello? Is it clear?
So may you repeat yourself one now?
Where am I repeating?
On the normal force, the part of normal force.
Which part here? Equation number 1, equation number 2, equation number 3, equation number 4. Which one do you want me to repeat?
Equation number 2, sir.
Equation number 2. Do you understand what this is? Here we are trying to find the resultant force along the y direction. The resultant force is equals to the sum of the forces acting along the y direction, which is this. From the choices we have made, any force pointing above the incline, in this case the normal, that's a positive force. Any force pointing below the incline, that is a negative force. So this force, the normal force, is pointing above the incline, it's positive. Then the other force, Samson Mwanza, can you switch off your microphone? So the normal force here is pointing above the incline, so it's a positive force. Then this component of the weight, mg cos theta, is pointing below the incline, so it's a negative force. So this is the result of the choices we have made. So our resultant force along the y direction is the sum of the normal force, which is pointing above the incline, plus this bit, mg cos theta, it's pointing below the incline. Any force pointing below, we give it a negative sign. So we end up having a resultant force which is equals to the normal force minus mg cos theta. So this is the expression of the resultant force. Fn minus mg cos theta is the resultant force along the y direction. However, you will notice that along the y direction, the position of the box or its velocity, they don't change, since the box will only tend to slide along this incline. So its height will not change, and also its velocity will not change. It will just slide along the incline. So the height from the incline won't change. The height is the same. The velocity is also the same. So that means that the acceleration along the incline in the y direction is equals to 0. If the acceleration is equals to 0, then we can write this expression for Newton's second law of motion, where you have the resultant force along the y direction equals to the mass multiplied by the acceleration, but the acceleration is 0. So the mass multiplied by an acceleration of 0 gives you 0. So this part, m times m, the mass multiplied by the acceleration along the y direction, this gives you 0. For this other bit, we substitute for our expression which we have here, which is Fn, which is equals to minus mg cos theta, and that's what we end up with here. We end up with Fn minus mg cos theta equals to 0. Since there's a 0 on this side, you take this bit to the other side, you end up with a normal force which is equals to mg cos theta. So this is how you get the normal force from an incline. The reaction of the incline to the weight which has been put there is going to be of a size m multiplied by g, which is the weight of the box, multiplied by the cosine of the angle which the incline makes. Are we clear?
Yes, sir. Very clear now.
Okay. Next.
Sir,
Yes.
excuse me, sir.
Yes.
So we can't be asked the question to calculate the friction.
The what?
The friction. We can't be asked to calculate the friction.
We are coming to that. Don't rush on. So next, we turn our attention to what's happening along the x direction. Yes.
So, why is the y component of the weight called the not sign?
It's because of the choice we made. Here. If you look at this, mg, this angle here is theta. If this is mg, this angle is theta, then you can see that you end up having this. This is going to be mg cos theta. This one is going to be the opposite. So the opposite of this angle is going to be mg sin theta. The adjacent of that angle is going to be mg cos theta. So it's just a matter of geometry. And because of the fact that the weight is always pointing down, so you end up having the y component as mg cos theta and the x component as mg sin theta. So there's a bit of a reverse here to what you're used to. Is that clear?
Yes, sir.
Yeah, it's a matter of just,
Clear.
yeah, geometry. Okay. Next, so we concentrate on what's happening along the x direction. So along the x direction, there are two forces. There's mg sin theta trying to put the box down. Then there's the friction force trying to put the box up, stopping the box from moving down or sliding down. So the friction is pointing up. We have decided earlier to say we are going to choose the direction in which the box is likely to move, which is down, to be the positive direction, and the other direction, if this is going to, so the downward motion of the box, if this is going to be the positive direction, positive x direction, then it means that the other side, which is the upper part, is going to be the negative x direction. So if that's a choice, then you see that this force, mg sin theta, is going to be a positive force, and the friction force is going to be a negative force. So using this mg sin theta, which is the x component of the weight, and the friction force, we can work out the resultant force along the x direction. So the resultant force along the x direction is going to be equals to the mg sin theta plus minus friction. So this is going to give us a resultant force along the x, which is equals to mg sin theta minus the friction force. Okay. Now, recall that whether the box decides to stay stationary or the box decides to move, the friction force is always given by the coefficient of friction multiplied by the normal force. So instead of writing this friction here, we replace that friction with an expression of the friction force using the coefficient of friction and the normal force. So our resultant force along the x direction becomes mg sin theta minus the coefficient of friction multiplied by the normal force. So in this case, when we reach this stage, there are two things which can happen. The first one is that the box remains motionless, and the second one is that the box slides. There are two things which can happen. The box remains motionless and the box slides. If you have ever tried to move along an incline, you cannot move at constant velocity unless you apply brakes. So in this case, there are no brakes being applied. It's just a box by itself. So it's either it remains motionless, it doesn't move, or it slides. If the box remains motionless and does not slide, we know that the acceleration along the x direction will be 0 because the box has decided not to move. So the acceleration is going to be equal to 0 along the x direction. So with that information, we write an expression for Newton's second law of motion along the x direction, which is going to be this: the resultant force along the x direction equals to the mass multiplied by the acceleration. However, as we have said, the box has decided to remain motionless. So if it remains motionless, then we know the acceleration of an object which is at rest. The acceleration is equal to 0. So in that case, this ax becomes equal to 0. We have this expression here, the sum of the forces, which is this mg sine theta, like that. So when you substitute here, you end up having the mass multiplied by an acceleration of 0 meters per second. That gives you 0. Then we replace for the resultant force, which is this one, which is mg sine theta minus Fn. So we end up having mg sine theta minus, because the box has decided to remain motionless, now our friction is going to be a static friction. So that static friction, you have to work it out using the coefficient of static friction multiplied by the normal force equals to 0. So you have mg sine theta minus static friction, which is mu s multiplied by Fn, equation 12. There's on the other end there, there's a 0. So you get this part, take it to the other end, you end up having mg sine theta equals to mu s, the coefficient of static friction multiplied by Fn. Now on this incline, remember we found an expression for the normal force. The normal force is equals to the weight of the box mg multiplied by cos theta. So we replace for this expression here. When you replace for that expression, we end up having mg sine theta equals to mu s multiplied by Fn. So if you replace for Fn, we end up having mg sine theta equals to mu s mg cos theta. On both sides, there is mg, so we divide on both sides by mg cos theta. So this side, if you divide by mg cos theta, and that side by mg cos theta, we remain with mu s, which is the coefficient of friction, is going to be equals to mg sine theta divided by mg cos theta, which is going to give you sine theta divided by cos theta, and sine theta divided by cos theta is just tan theta. So the coefficient of friction, the person was asking to say, how then do we find the friction force? For you to find friction, you need to know what the coefficient is of friction. So in this case, when your box remains motionless, the coefficient of static friction is equal to the tangent of the angle of the incline. That's equation number 15. That's how you find the coefficient. Once you find the coefficient, then you can always work out friction. Once you know the coefficient, once you know this, then of course we know how to find this, which is what we have here, mg cos theta. You can find those things there, then you can find what the friction is. So we can ask you to say, what is the friction force? What is the value of the friction force keeping the box motionless? You will need this. You need to find the coefficient of friction by working out this tan theta. Tan theta will give you the coefficient of static friction. Then you can use this coefficient together with the normal force here, which normal force is given by this, to find what the friction is. Are we clear? Here, 15. Is it clear? Okay, so with this information, the angle at which your object stays motionless, that is what is called the angle of friction. And that angle of friction, if we have given you, if you have been given this coefficient of static friction, you can find what the angle is. The angle is going to be theta, is going to be the tan inverse of the coefficient of static friction, or the arctan of this. That's what the angle is going to be. The angle of the incline. So it's either we give you an angle of the incline, or that angle is not you're not given that angle of incline, and we ask you to find the angle of the incline. Yes?
Can you use the same angle to find the coefficient of kinetic friction?
No, you can't. This formula only works. This formula only works if the box remains motionless. Are we clear?
Oh, all right.
Yes, if the box remains motionless, then you can use this formula. If the box, on the other hand, decides to slide, if the box begins to slide, slowly, then faster and faster, because that's how things slide on an incline. Something starts off slowly, then its velocity starts to increase. By the time it reaches the bottom of the incline, something is moving very, very fast. The reason why it's moving very fast is because there is acceleration. So on an incline, you cannot, on your own, move with constant velocity. There are only two options. Either you remain motionless, or as you go down the incline, your speed increases. Those who have tried to go down inclines, they know what happens. You literally have to put effort to try to kind of like, I don't know how, to make yourself fall a bit, otherwise you're going to fall forward. You have to try to make yourself fall backwards. Okay? And you do this because you're trying to go down the incline at constant velocity. So you have to do something for that. Okay? So if the incline is going to slide and the velocity of the incline of the object increases, then it means that there is acceleration, and in that case the acceleration is not equal to 0. If the object slides down an incline on its own, under its own weight, it means that there is acceleration, because the velocity of the object will increase as the object goes down. So how do we find the acceleration in this case? We have to go back to Newton's second law of motion along the incline. So we have the resultant force, which is the Fx. Then we have the mass of the objects and the acceleration we are looking for here. So we write this expression. Now in this case, the resultant force is equals to the expression for resultant force along the x direction. This is what we have: the mass of the box, sine theta, minus mu multiplied by the normal force. Now in this case, the box is moving, so the friction is not going to be static friction, but kinetic friction. So we end up having the mass, the weight multiplied times sine theta, minus mu k, which is the coefficient of friction, multiplied by the normal force, equals to the mass times the acceleration. Then for this normal force, we have a replacement expression, which is what we did here, which is the, where is that? This mg cos theta. So we replace for Fn, we put in mg cos theta. So when you do that, we end up having mg sin theta minus mu k, then mg, then multiplied by cos theta, which is going to give you the mass times the acceleration. Now, as long as the acceleration of a particular object is increasing, our interest is, as long as the velocity of an object is increasing, our interest is to find the acceleration. And that's what you're going to do here. So we are going to divide both sides by the mass so that we can find an expression for acceleration. So when you divide this side by the mass, you divide this side by the mass, you end up having ax being equals to mg sin theta minus mu k mg cos theta, like this, divided by m. So this side you divide it by m, this side you divide it by m, so you end up having mg sin theta divided by m mu k mg sin cos theta divided by m. When you divide the m this side and that m, they go, this m and that m, they go. So you remain with g sin theta minus mu k g cos theta. So what do you see here with this expression of acceleration? It is telling you that when an object is on an incline, the acceleration of that particular object does not depend on the mass. Because as you can see in this expression of ax, there is no mass in this expression. The only things you have, there is a g. The g is because the acceleration due to gravity is because we are on earth. Then there is a theta. The theta is the angle of the incline. Then there is this mu k. Mu k is the coefficient of kinetic friction. The coefficient of kinetic friction depends on how smooth the whole thing is. So there is a g part here, there's g here, so you can factor out the g. So when you factor out the g, we end up having ax, which is the acceleration along the x direction, is equal to g, then sin theta minus mu k cos theta. This. So this is the general expression of acceleration along an incline. The acceleration along the incline is equal to g open brackets sin theta minus mu k cos theta. That is the acceleration. How does this expression actually work? Well, we can choose, for example, if our inclined surface does not have any friction, if we assume that this inclined surface does not have any friction, if there is no friction on this inclined surface as the box is moving, it means that the coefficient of friction is equal to 0. That's what it means. If the coefficient of friction is equal to 0 here, then it means that this part, mu k cos theta, disappears. So the only part you're going to be left with is going to be g sin theta. So if your inclined surface is frictionless, it has got no friction, then in that case, what you end up with is ax is equal to g sin theta. If on the other hand, is it clear what you have here? Equation number 24 and 23. If the surface is frictionless, it doesn't have any friction, then the coefficient of friction is going to be 0. Otherwise, if there's friction, then the coefficient of friction will not be equal to 0. So in this case, we are assuming that we tell you to say, oh, this particular object is sliding on a frictionless surface. If it's sliding on a frictionless surface, then the coefficient of friction, kinetic friction, is equal to 0. If that's the case, then this part disappears because you're going to have a 0 multiplying the cos. So the only thing you're going to remain with is g sin theta. So this is going to be equal to your acceleration. So your acceleration would depend on the acceleration due to gravity, which you can't change. So meaning that the acceleration just depends on sin theta. If, on the other hand, we get tired of the inclined plane, the way it is, like this, then we decide to change this inclined plane into a flat surface. So we make this angle theta equals to 0. If theta becomes equals to 0, if that's what happens, if theta becomes equals to 0, so our inclined surface now becomes just a normal flat surface. So the angle is going to be equals to 0. This angle theta will be 0. So we end up having ax equals to g sine 0 degrees minus mu k cos 0 degrees. Now, sine 0 degrees is equals to 0 and cos 0 degrees is equals to 1. So this part, this one will disappear. The sine will disappear. So this part here is going to be 0. Then this cos 0 is going to be 1. So the only thing which is going to be left here is going to be the minus mu k. So you end up having acceleration ax equals to minus mu k. Now, this is very interesting because this is the acceleration minus mu k. Why is it interesting? Once you have the acceleration, you can multiply the acceleration by the mass. So if you multiply this acceleration ax by the mass, what you end up having is minus mu k, then g multiplied by m. The g multiplied by m is just the weight of the box, which will be equal to the normal force. So we get back to what we had yesterday. Are we clear?
Yes, sir.
Next, if you decide to make the angle of the incline become 90 degrees, if the angle of the incline becomes 90 degrees, meaning that if you push the incline up, this incline up, so that the angle becomes 90 degrees like this, like that. If the angle becomes 90 degrees, in that case, your expression undergoes a bit of change. So you end up having ax equals to g sine 90 degrees minus mu k cos 90 degrees. Sine 90 degrees is equals to 1. Cos 90 degrees is equals to 0. So you end up having mu k multiplied by 0. So this part gives you a 0. Then this part here gives you 1. So you end up having 1 minus 0 is 1. 1 multiplied by g. This gives you your acceleration as g. So if your incline is like the way the wall of a house is, it's at a 90 degrees, then that particular mass will just fall with acceleration g. It doesn't matter, it's just going to fall with g, acceleration. Is it clear? So you can play around with this expression of acceleration. Equation number 23, very, very important equation, because it tells you what the acceleration is along an incline. It is equals to g, open bracket, sine theta minus mu k cos theta. Depending on what you have, if your incline is frictionless, then mu k is going to be 0. If you decide to go back to a normal flat surface, then theta is going to be equal to 0. If you decide to raise your incline so that it becomes a wall, then theta is going to be 90 degrees. In both cases, if your surface is frictionless, this is going to be the acceleration. If you decide to make your incline to be at an angle of 0 degrees, then this is going to be the acceleration. If your incline stands like a normal wall, then your acceleration is just going to be equal to g. Is this clear? The only thing we're interested in is acceleration, because once we know the acceleration, everything else can be predicted. Are there any questions? Any questions?
Yes, sir.
The one thing, yes, go ahead.
Yeah, then how do you know that the box of the incline plane is sliding or stopping?
We are going to tell you that it's sliding.
When we have been given the
We are going to tell you the box is motionless or it's sliding. So if it's sliding, you know it's moving.
Yeah.
If it's motionless, you know it's stopped. We'll tell you.
No.
Any other question?
Thank you, sir.
Yes. Okay. So, this formula we usually give it. We usually give you this formula. So when you see it, you should know, because we are going to give you a sheet of formulas when you're writing your exam. So when you look at these formulas, you should have an idea what these formulas do and what they're used for. If you just look at this formula, then you don't have an idea what it is. You cannot use it when we give you an incline problem to say, oh, what is the acceleration of this thing? or how far is it going to be after 2 seconds? If it starts off from 0, then after 2 seconds or after 3 seconds, how far is it going to be, and with what velocity is it going to be moving? For you to answer the question of how far a box is going to be along the incline and with what velocity it's going to be moving, you need to know the acceleration of that particular box. You need to know the acceleration, you need to know the initial velocity. Since it started from motionless, you know that the initial velocity is 0. But for you to predict, you need acceleration. Are we clear?
Yes, sir.
Okay, unless there are any questions, we'll stop here. We have used up our time. Any questions?
So, sir, the same formula, is it used to find only the acceleration?
Yes, it's only used for acceleration. What else do you want to use it for? We are in the business of acceleration. That's what we want. If the velocity is changing, we want to know the acceleration, and that's what this is used for. You use this for finding acceleration on an incline. Any other question?
And what about the other formula, the applied force is equals to mass times acceleration? You can't use that to find acceleration.
What do you think you have been using all this time?
The same formula, sir.
This. What do you think this looks like?
The resultant force.
What's the difference? What do you think the F? The F in F is equals to mass times acceleration. That F is the resultant force.
Alright.
Yes. Any other question? Okay, so I'm sure I saw people looking at tutorial questions on something on this stuff, so something will come up definitely, then you can use this information there. There is one other thing which I think I need to prepare just roughly tomorrow. This is concerning the motion of coupled system. So how does this whole thing come into being if you've got a coupled system? So yeah, so I need to see if I can prepare for that tomorrow so that we are ready for the quiz on Monday. So unless any other questions, we'll stop here. I'll stop sharing. And the recording is going to be uploaded to YouTube as usual. Okay, so I'll see you tomorrow.
Thank you.
Cheers.